In the desert of California, a small team believed rockets could be reinvented from scratch. Elon Musk had just sold PayPal, and he wanted to make humanity a spacefaring species. In 2002, he founded SpaceX with a wild goal: cut the cost of spaceflight forever. Back then, rocket engines were built like fine china, expensive, fragile, and used only once. NASA and old aerospace giants spent hundreds of millions on a single engine design. Musk asked a simple, dangerous question: what if we built engines like factories build cars? His first engineers thought he was crazy, but crazy ideas were exactly what rockets needed. The team started with something small and simple: a kerosene engine called Kestrel. Kestrel powered the upper stage of Falcon 1, SpaceX's very first rocket. But the real challenge waited below, in the engine that would lift the whole vehicle. That engine needed a name worthy of ambition, so they called it Merlin. Merlin burned refined kerosene and liquid oxygen, a proven combination, but built completely differently. Instead of custom, one-off parts, SpaceX designed Merlin to be manufactured again and again. They used a gas generator cycle, simpler and cheaper than the exotic engines of the past. Simplicity was the secret weapon. Fewer parts meant fewer failures and lower costs.
In 2006, Falcon 1 lifted off for the first time, powered by a single Merlin engine.
It failed just seconds after liftoff. A fuel line fitting had corroded and cracked. The rocket tumbled into the Pacific, and skeptics called SpaceX a doomed experiment. Musk had spent nearly his entire fortune, and failure was not just embarrassing, it was existential.
A second launch followed in 2007, but a fuel slosh problem shut the engine down early.
The rocket reached space this time, but never made it to orbit.
A third attempt in 2008 ended when the new engine's leftover thrust caused a stage collision.
3 failures in a row, and SpaceX had almost no money left to try again. Employees worked without knowing if their paychecks would clear the following month. Musk gathered his engineers and asked for one more shot, one final rocket.
On September 28, 2008, Falcon 1 lifted off for the 4th time.
The Merlin engine roared clean, the stages separated perfectly, and Falcon 1 reached orbit. It was the first privately built liquid-fueled rocket ever to reach orbit successfully. That single success saved the company and proved the engine concept actually worked.
But orbit was only the beginning. The real target was reusability, not just launch.
Every rocket in history had been thrown away after a single use, like a paper cup. Musk believed that was the reason spaceflight stayed so brutally expensive for decades.
If airplanes were destroyed after every flight, plane tickets would cost millions of dollars.
So SpaceX set out to build a rocket engine that could fire, land, and fire again. This meant redesigning Merlin to survive repeated ignition, re-entry heat, and violent landings. Engineers upgraded Merlin into the Merlin 1D, lighter, more powerful, and more efficient. The 1D could throttle its thrust up and down, a skill essential for a soft landing.
9 Merlin engines were clustered together at the base of the new Falcon 9 rocket.
That clustered design meant even if one engine failed, the mission could often still continue.
In 2012, Falcon 9 carried the Dragon capsule to the International Space Station successfully.
It was the first commercial spacecraft in history to dock with the space station. But landing a rocket booster back on Earth was still an unsolved, terrifying problem.
SpaceX built a strange testbed called Grasshopper, a rocket that only flew straight up and down.
Grasshopper hovered, climbed a few hundred feet, and gently set itself back on the pad. Engineers were teaching a rocket to do something no rocket had ever done: land itself. Grid fins were added, small wings that could steer the falling booster through the air. Old gas thrusters flipped the rocket around after separation, aiming its engines toward home. In 2013, SpaceX attempted real landings on the ocean, using a floating platform as a target.
The first ocean landing attempts ended in fiery explosions, but each failure taught something new. One booster ran out of hydraulic fluid controlling its grid fins moments before touchdown.
Cameras captured the rocket spinning wildly before slamming into the water in a fireball.
Musk posted the footage publicly, turning a costly failure into a viral, honest lesson.
Engineers called their landing platform a drone ship and gave it playful, sci-fi names. One was named, "Of Course I Still Love You," a nod to a science fiction novel. Attempt after attempt, boosters crashed, tipped over, or exploded just above the deck. Each failure was studied frame by frame, data pulled from every sensor on board. In December 2015, everything finally came together during a critical satellite launch mission. Falcon 9 lifted off, delivered its payload, then reignited its engines to return home. The first stage descended through darkness, grid fins slicing the night sky. It touched down upright on solid ground at Landing Zone 1 in Florida. For the first time in history, an orbital rocket booster had landed itself intact. Engineers erupted into cheers, hugging each other in the SpaceX control room. It wasn't just a landing. It was proof that reusable rockets were truly possible. Months later, SpaceX landed a booster on the floating drone ship at sea. Landing at sea was even harder. The platform rocked gently with ocean waves.
In 2017, SpaceX relaunched a previously flown booster for the very first time.
That booster had already flown to space once, and now it flew again successfully. Rocket reuse, once dismissed as science fiction, had become an operational reality. Launch costs began dropping as boosters flew again and again with minimal refurbishment. Merlin engines were inspected, some parts replaced, and boosters were readied for their next flight. By the early 2020s, individual Falcon 9 boosters were flying more than 10 times each. What once seemed impossible had quietly become routine, almost boring in its reliability. But Musk was already dreaming far beyond Earth orbit, toward Mars itself. Kerosene-fueled Merlin engines were incredible, but they weren't suited for deep space missions.
A journey to Mars needed a completely new kind of rocket engine altogether. SpaceX engineers began designing a radical engine unlike anything flown before, calling it Raptor. Raptor would burn methane and liquid oxygen instead of kerosene, a bold departure.
Methane, unlike kerosene, could theoretically be manufactured on Mars using local resources.
That meant future starships could refuel on Mars for a trip back to Earth.
But the real innovation in Raptor was hidden deep inside its combustion cycle.
Most rocket engines burn fuel richer or leaner to keep components from melting.
Raptor used something called full-flow staged combustion, the most efficient cycle ever attempted.
In this cycle, all the propellant passes through preburners before reaching the main chamber. Both fuel and oxidizer are turned to gas separately before they ever fully combine.
This design keeps turbine temperatures lower, reducing wear and increasing engine lifespan.
Only a handful of full-flow staged combustion engines had ever been built worldwide.
Soviet engineers had experimented with the concept decades earlier, but never flew one. SpaceX was determined to be the first company to actually launch one into space. Raptor operated at chamber pressures higher than any rocket engine in history. Higher pressure meant more thrust, squeezed from a smaller, lighter engine package. Building something this complex meant constant testing and constant, spectacular failures. Test stands in Texas shook as early Raptor prototypes ignited, sputtered, and sometimes exploded.
Engineers reviewed failure footage and the same way crash investigators studied airplane wreckage.
Turbopump failures, chamber cracks, and fuel leaks each demanded their own painful lesson.
Rather than slow down, SpaceX embraced rapid iteration, building and testing new engines quickly.
Their philosophy became famous: fail fast, learn faster, and never fear a fiery mistake.
Each Raptor version improved on the last, becoming lighter, simpler, and more powerful. Raptor 2 cut manufacturing complexity dramatically while boosting thrust output significantly. What once took months to build began taking mere days on the production line.
Raptor engines were now assembled almost like industrial machinery, not delicate spacecraft parts.
This engine would power Starship, the largest and most powerful rocket ever built.
Starship's Super Heavy booster used dozens of Raptor engines clustered at its base.
No rocket in history had ever flown with that many engines firing together. Coordinating dozens of engines demanded software as sophisticated as the hardware itself. Sensors monitored every engine thousands of times per second, ready to shut down failures instantly.
In 2023, Starship attempted its first full integrated test flight from Texas.
Several Raptor engines failed during ascent, and the vehicle tumbled before self-destructing.
Instead of despair, SpaceX called it valuable data and began preparing the next attempt.
Later flights saw more engines survive, and the rocket flew further each time. Eventually, Starship reached space and demonstrated controlled re-entry through Earth's atmosphere.
The booster even returned to the launch site, caught mid-air by giant mechanical arms.
Watching a rocket booster fall from space into a pair of waiting arms stunned the world.
It looked like something from a movie, but it was real engineering, tested repeatedly. Every explosion along the way had quietly built toward this improbable, precise moment. Raptor's efficiency meant Starship could one day carry massive cargo, or even people, to Mars.
Musk often said rockets should be as reusable as commercial airplanes, refueled and reflown daily.
That vision demanded engines that could fire dozens, even hundreds of times without failure.
Merlin had proven reuse was possible, and Raptor was built to make it routine.
The story of these engines is really a story about relentless, disciplined failure.
SpaceX didn't succeed by avoiding mistakes. It succeeded by making mistakes cheaply and quickly.
Traditional aerospace companies tested designs on paper for years before ever lighting an engine.
SpaceX instead built hardware fast, blew it up, and used the wreckage as a teacher. This approach shocked traditional engineers who valued caution over speed and iteration.
But it produced engines that evolved faster than anything the industry had seen before.
Cost per engine dropped dramatically as production shifted from custom parts to mass manufacturing. Merlin engines, once expensive prototypes, became almost assembly line components by the 2020s. Raptor followed the same trajectory, shifting from delicate lab hardware to rugged production units.
Lower engine costs meant lower launch costs, and lower launch costs changed the entire industry. Satellite companies that once waited years for a launch slot suddenly had regular access to space. Scientific missions that seemed financially impossible became affordable and achievable within a single decade.
NASA itself began relying on SpaceX engines to carry astronauts to the space station.
It marked the first crewed orbital launch from American soil in nearly a decade.
The engines that once exploded on a barge were now trusted to carry human lives. That transformation, from failure reel to human spaceflight, captured the imagination of the world. Engineers who once feared for their jobs now stood proudly beside history-making hardware. Every successful landing carried the memory of every explosion that came before it.
Rocket engineering had always been conservative, but SpaceX proved boldness could still be safe.
Raptor's full-flow staged combustion cycle remains one of the most complex machines ever built.
Within it, propellants reach searing temperatures and crushing pressures in a fraction of a second.
Yet it must survive that violence again and again, launch after launch after launch.
This is the quiet miracle hidden inside every Starship liftoff. Precision born from chaos.
Few people watching a launch realize how many failures made that moment possible.
Behind every triumphant landing sits a graveyard of test stands, twisted metal, and lessons learned.
SpaceX turned rocket engineering from a slow, secretive craft into a fast, public spectacle.
Live-streamed explosions became bizarre entertainment, teaching millions of viewers real aerospace engineering along the way.
Kids who grew up watching landing failures later applied to work at SpaceX themselves.
The company didn't just reinvent an engine, it reinvented how engines get invented.
Musk's obsession with Mars pushed engineers toward solutions no customer had ever demanded before.
Methane fuel, full-flow combustion, and rapid reuse all trace back to that single, distant goal. Getting to Mars meant engines had to be radically more efficient than anything before them.
Every design choice, every failed test, pointed toward a rocket capable of interplanetary travel.
Today, Merlin engines have flown hundreds of missions with remarkable, growing reliability.
Raptor engines are still evolving, chasing higher performance and simpler manufacturing every year.
What began as a desperate startup with 3 failed launches now dominates global spaceflight.
Competing nations and companies have been forced to rethink their own engine philosophies entirely.
Reusability, once mocked as impossible, is now the expected standard across the industry. The rocket engine, one of humanity's oldest and most stubborn machines, was reinvented in decades.
It took explosions, bankruptcy scares, and relentless iteration to get there.
And it all started with one small kerosene engine, refusing to give up on the sky.